Okay, right. So right. So we said we had n Bernoulli trials. Okay. Now we say each xi is a Bernoulli. Each xi is Bernoulli p, which means by this we mean xi takes on values 0 or 1, and the probability xi equals 1 is p. Okay, and we also saw that the xi okay, the random variables xi are also given to be independent. Okay, so here what is the universe? Last class we said we are going to use all possible combinations of outcomes of x1 through xn as our universe. Okay, what will be the universe? Right, so what will be the universe in this case? Yeah, so the set of all binary sequences right, so the n-fold Cartesian product of 0 1. Okay, uh, right, so this is the universe. What is the probability x1 through xn is, let us say 1 1 1. What's the probability that the sequence equals this specific sequence? The first k elements are the first k outcomes, first k trials all give 1, the remainder n minus k trials all give 0. Right, so they are independent. Right, so how do we write this? Okay, so this is an intersection of various outcomes, so we would write it as probability x1 equals 1, probability x2 equals 1 given x1 equals 1, all the way through probability xk equals 1 given x1 through xk minus 1 equals 1 1 1 times the probability xk plus 1 equals 0 given x1 through k is 1 1 1. And right, so here when we write all of this, right, so so independent, so this is always true. Independence means, right, so independence will tell us that all these probabilities, the conditional probabilities, will be equal to their marginals. So we simply have right, now there are, this is p p p, there are k of these, and 1 minus p to 1 minus p, n minus k of these. And so we have 3 to the k times 1 minus k to the n minus k. Right? So this is the probability of this particular sequence. Okay. Now, one thing you notice is that if you rearrange the order, if you permute the sequence, okay, if you rearrange the order of ones and zeros, um, uh, just 1 second. Okay, so if you rearrange the order of this sequence, okay, so you move the ones and zeros in any order, okay, then you'll still have the same working. You'll work out things in the same way. Okay, you'll still get a product of n terms, and exactly p of them will be one, and exactly k of them will be one, and n minus k of them will be 1 minus p. Okay, so any sequence, any individual sequence with exactly k ones and n minus k zeros will have probability p to the k 1 minus p to the n minus k. Okay, so this is how the probability distribution looks like. Okay, and so while we haven't enumerated all these 2 to the n sequences and their individual probabilities, we have done something effectively similar. Okay, any sequence we are given, we know how to write the probability. Okay, and so in that manner, we have written the probability of any point in the universe, any outcome in the universe. So is this clear? Okay. Uh, is this clear? So I can't really see anyone, so I'm just going to assume something. Okay. Uh, okay. Okay. So right. So this will be the probability of sequences. Okay. And we last class, and this is still material from last class. We also constructed a new random variable. Right, so y, which is the summation of x1 through xn, right? So in effect, if you take a sequence with exactly k ones, okay, and n minus k zeros, right, so y will turn out to be 1 plus 1 plus 1 k times, and the rest of them are zeros, so they don't add anything to the sum. Okay, so y counts the number of ones, right? So y counts the number of ones in the sequence x1 through xn. Okay. Now, so last class we also said that the event y equals k. Okay, this corresponds to all binary sequences with exactly k ones, right? And we also saw that the number of sequences with exactly k ones is n choose k. Okay, so is everyone on board with it till here? Okay, so what is the probability y equals k? So this is new. Okay, so till here we did last class, but if you follow everything so far, you should be able to answer this. What's the probability y equals k? Okay, very good. So anyone else? So all of you said, or either you didn't respond or you said you understood. So is everyone clear why this should be so? Okay, the probability y equals k is n choose k times p to the k 1 minus p to the n minus k. Okay, is everyone completely okay with this? Okay, so because if you truly mean what you said or did not say, and I'm forced to assume that you're following along because I get no response, right? So there's only one thing I can do. But if you truly mean that, this should be immediately obvious. If it's not immediately obvious, we have to go back, and I need your help to figure out where there is a gap. Okay, so how many of you see this immediately? Okay, uh, okay, so some of you do not. Okay, so okay, so let's go back. So is this clear? Like the probability of a single sequence that has okay, so is this part clear? Okay, so the probability of any sequence, okay, any single sequence with k ones, okay, has to be p to the k times 1 minus p to the n minus k, right? So for those of you who are right, so Axel or Adriana, like, is this part clear?
Yeah.
Okay, so for both of you this is completely okay. Okay, so also for others who are having trouble with this, uh, uh, so you need to tell me in order so that I can go back to where it is that you have an issue. Okay, so is this part clear for everyone? Right, so okay, so I actually don't see anything from anyone. Uh, right. So Quinn, Preston, George, yeah, some of you I see, but most of you have no response. So one way or the other. So they can't. I mean, a statement and its converse and its negation cannot both be true. But in any case, okay. So let's continue from here. Okay. Uh, so y equals k is the event that contains all. So y equals k. Y counts the number of ones in a sequence. Okay. So y equals k is the set of all binary sequences with exactly k ones. Okay. So does that make sense?
Yeah, that makes sense.
Right. Okay. So and also we did this last class. The size of y equals k, the event y equals k is n choose k. Okay, so the number of sequences in this set is n choose k.
Yeah, that makes sense. I think the hardest part is like the last step, putting that together.
Okay, so here, like, how do we write the probability y equals k? Okay, so to write the probability y equals k, we are doing it just like any other. So actually, we'll do a specific numerical example, but after this, okay, and then probably it will become more clear. But I want you to try and figure it out before we do the numerical example. Okay, when we write the probability y equals k of the event y equals k, like we are doing exactly what we have been doing in the past. Okay, the difference now is that we are trying to do this in an abstract manner, right? How did we write the probabilities of events before? What we did was we looked at every row which corresponded to that event and added up all their probabilities, right?
Hmm.
So we said, okay, this we wrote it as a disjoint union of so we wrote it as a sequence of, here y equals k is a set of many sequences. In fact, there are exactly n choose k such sequences. Okay, now what those sequences are exactly sequences. They're all these sequences with exactly k ones. Okay,
Hmm.
they have k ones and n minus k zeros, right? So this event y equals k contains all these n-choose k sequences, right?
Mhm.
So all we have to do is go and add up the probabilities of all these sequences. Okay, so we write it as a disjoint union, right? So we are doing exactly like what we did before, but we are just doing it abstractly. Okay, now what is the probability of any one sequence with k1s and n minus k zeros? Right, so that is exactly the calculation here.
Yeah.
Right, so any one sequence with k1s and n minus k zeros is p to the k times 1 minus p to the n minus k, and this is true no matter which sequence it is. Okay, so long as it has exactly k1s and n minus k zeros.
Mhm.
Right, so we add p to the k 1 minus p to the n minus k. So there are n choose k terms, each of which is p to the k times 1 minus p to the k. Right? And so that's why this probability is n choose k times p to the k times 1 minus p to the n minus k. Okay, so does this make sense?
Yeah, that makes sense now.
Okay,
Thank you.
so in effect, like one thing to note is that once we have written out these probabilities, once we did this, okay, once we wrote out the probabilities of events in the universe, there's only one thing we know how to do. Okay, we may do it in more and more sophisticated ways, little more abstractly and so on, but in a sense, we are doing exactly the same calculations over and over again. Okay, when we write the probability of an event, we see what all outcomes belong to an event and write out the probabilities of each of these outcomes. Okay, that's what we have done here, and that's what we'll keep doing throughout. Okay, there's never going to be anything different. Okay, the good thing is there's never going to be anything different from this. The bad thing is like we have to use it in more and more abstract ways. Okay, so but Adriana, are you good on this? Okay,
Yes.
okay, thank you. Right, so we can go over any of the prior things because there are very few concepts. It's only a question of putting them all together, and that is non-trivial. That's highly non-trivial. Okay, so let's do a specific example here. Um, okay, so let's go back to our simple case where n equals 3. Right, in this case the universe is the set of all length 3 binary sequences, right, and which we have written many times, right, and also the probabilities now are, so I'm going to write this order, uh, maybe I'll write it the same way. Yeah, I'll do it in 2 steps. Okay, so first we just write it the same way we have been writing before. Right, so we want all the probabilities, right? So in the probability here is 3 zeros, so 1 minus p. So let me write the number of ones and the number of zeros. Okay, so this is x1, x2, x3. Okay, this is the number of ones. This is the number of zeros, which will be n minus k. Okay, so here the number of ones in the sequence 0, 0, 0 is 0. Okay, the number of ones here is 1. Okay, the number of 1. How many ones here? 2, 1, 2, 2, 3. Okay, so sorry, this is y. Right, and the number of zeros here is 3, 2, 2, 1, 2, 1, 1, 0. Okay, so this will be the number of zeros. The probabilities are p to the 0, 1 minus p to the 3, p times 1 minus p squared, p times 1 minus p squared times 1 minus p times 1 minus p squared times 1 minus p squared times 1 minus p, and p. Okay, so is everyone okay with this? So this is how we wrote the probability. So when we wrote that one line, that the probability of any sequence with exactly k1s is p to the k 1 minus p to the n minus k, it is equivalent to writing out this entire table like this. Okay, so that's exactly what we did. We just did it a little bit abstractly. Okay, now this is the number of ones, this is the number of zeros, but I'll write it again. Like the random variable y counts the number of ones, so it's exactly this column. Okay, so but I'll write this again. Okay, so y just counts the number of ones. Okay, and sure enough, you can verify this is x1 plus x2 plus x3. Okay, right, so here it is 0 plus 0 plus 0, so here it is 0 plus 0 plus 1. Okay, and as you see, every time a 1 appears in the sequence, it contributes, it adds 1 to y. Okay, zeros don't add anything to y, so this will just count the number of ones. Okay, so is everyone okay with this? Right, so the event y equals 0, right, so this has size 3 choose 0. Okay, and this is 1, right, and that is exactly this time. Right, so this event in blue is the event that y equals 0. Okay, now the event y equals 1 has size 3 choose 1, and that is 3. And what is the event y equals 1? So can someone help me, like what's the event y equals 1? Right, so these two outcomes. Okay, what else? Right, and this. The three outcomes in green, okay, the three outcomes in green correspond to the event y equals 1. Okay, they're all the rows where I see y equals 1. Okay, and this corresponds to every way you can write a sequence of length 3 by placing exactly 1 ones. Okay, and if I see the locations where 1 is placed as a subset of 1 2 3, it's a one-sized subset of 1 2 3. Okay, now let's look at the event y equals 2. Now this has size 3 choose 2, which is also 3, and this event, so what is this event? Y equals 2. Very good. Right, so those are the outcomes in red. Okay, and finally, like y equals 3, is the remain, this has size 3 choose 3, which is 1. Okay, and it is the one event in, oh, okay, so this is the y equals 3 is the one outcome in black. Okay, so this is what is happening. Okay, so the values of y partition the universe. Okay, the values of y partition the universe into various subsets. Okay, and the events are y equals 0, y equals 1, y equals 2, and y equals 3. Okay, and this in general, there'll be the events y equals 0, y equals 1, all the way up to y equals n. Okay, now the probability y equals 0. So when I think of the probability y equals 0, okay, this is of course like there's only one sequence. So it is 1 times p, it is 0, 1 minus p cubed. This is 1 minus p cubed. Okay, if I look at the probability y equals 1, when I look at the probability y equals 1, the thing to note is that the way we have assigned the probabilities, look at all the green elements. Okay, they all have the same probability, and that is p to the 1 times 1 minus p squared. Okay, so or in general, it will be p to the k times 1 minus p to the n minus k. Okay, and there are exactly 3 choose 1, or in general n choose k of these sequences. Okay, so the probability of this event y equals 1 is just p times 1 minus p squared added 3 times, or in general added n choose k times, and this is 3. Okay, then same way the probability y equals 2 will be p squared times 1 minus p. And finally, okay, so does this make sense? Is everyone okay? Okay, so okay, so here, so these are so everyone is completely okay with this. Okay, so the random variable y, just like the random variables x here, right? So sorry, the random variables x here, right? We call them Bernoulli variables. Okay, the random variable y here also has a name. Y is called, so we write this to say that, so this means it is distributed as, okay, so this is just the description of the random variable. Okay, so y has a name, and the name is, it's called a binomial random variable. Okay, now when we write a binomial random variable, we pass in two parameters. Okay, one is the number of Bernoulli trials. Okay, and the other is the parameter corresponding to each of the Bernoulli trials. Okay, okay, now this is, like I said, like this template is actually very uh, it occurs in many places. It's very common. Okay, so in fact, like we have seen an example before, for which we can analyze it using this template. Okay, and let's go back to our prosecutor's fallacy. uh, right, so we analyzed many things here, but remember what the story was. There are 100,000 people in the town. There has been like some murder, and uh, the the prosecutor says, I mean the expert says that the DNA of the crime scene, or rather an innocent person's DNA will match. Okay, and when I said this, okay, so many of you actually said a statement that was very interesting to me, that you said that there are probably going to be two matches. Okay, even if everyone is innocent, there are probably going to be two matches. What you did was you multiplied 100,000 by 1 over 50,000. Okay, that's a very interesting thing to do, and we'll see what exactly that means, what the multiplication gives you. Okay, but everyone remembers this problem. Particularly, we don't need the entire problem, we just need this statement. Okay, let's imagine that, so imagine that all 100,000 are innocent. Okay, how many matches will you see? Okay, so let's imagine all 100,000 are innocent. How many matches will we see? Okay, so how will you answer this question? So at that time you said like you would see two matches. Okay, and Donovan, you're saying two. Okay, will it always be two? Will every town with 100,000 people with this test have exactly two matches? No, right? Some towns may have more purely by accident, some towns may have fewer, right? Right, so but how many, what is the maximum number of matches? We're not concerned about whether it is likely or not. Okay, but what's the maximum number of matches possible? Right, so it is, so this is a very important point, that's very good. Okay, so it is by this test, like by the statement of this test, it is completely possible, just not very probable. Okay, it is completely possible that all 100,000 people may match the DNA on the crime scene. Right, it is completely probable that may happen. Sorry, it's completely possible that that may happen. Okay, it's also possible that no one will match. Okay, it is also possible that one person will match, it is possible two people will match, three people will match, four people will match, and anything. Okay, so any number is possible, any number of matches is actually quite possible. Okay, so how do we think about this? Can, given that, given the context that we are talking about independent Bernoulli trials and binomial variables, okay, so let's try to analyze this. Okay, now let's imagine, and this is so let's make an assumption. Okay, so each test, okay, now this is an assumption that we can remove. Okay, but we are making this assumption simply to fit into something that we have seen, and we'll see how to remove this assumption. Okay, I'm writing this assumption because very explicitly I want you to think of this assumption, and I want you to think of, and we will see what will happen when you remove this assumption. Okay, now, so assume that each person's test is independent. Okay, now this is not a very realistic assumption. Okay, so people who are in the same family may, their tests may be correlated. Okay, it's possible that the equipment that's used to make this test somehow introduces dependencies between the tests. Okay, so many things are possible, but let's assume for the moment that each person's test is independent. So the result of whether this person's, so we are assuming all are innocent. Each time somebody goes to do the test, the result may come up to be match or not a match. Okay, it is match with probability 1 over 50,000 and not a match with probability 1 minus 1 over 50,000. Okay, now can you tell me how to model this given what we have been talking about so far? Okay, so here is where the Bernoulli trials come into play. Okay, so let us say, let's number the people 1 to, okay, so in some order, number all of them. Okay, so there are I is the number of a person, the label you give to a person, and this label can take values 1 to 100,000 in sequence. Okay, so let me just, okay, now, right, so let me just move to, I'm just going to move to the next page so you can have it continuously. So no change in what I'm writing, I'm just going to paste it here. Okay, so here, let's just number the people 1 to 100,000. Okay, and let me write by xi a random variable. This xi is 1 if persons, okay, xi is 1 if the person's DNA matches the crime scene and 0 else. Okay, now what do we have? So we have x1 to x 100,000. Okay, now probability xi equals 1. What is the probability xi equals 1? The ith person DNA comes as a match to the crime scene. Right, so this is 1 in 50,000. Right, so this is 1 in 50,000, which we called P. Okay, so we and we also know xi are independent because we just made that assumption. Right, so these are exactly independent Bernoulli trials. Okay, and y is the number of matches, right, and y is simply x1 plus x2, right, and so y is actually a binomial random variable with 100,000 trials, and p is 1 over 50,000. Okay, so under the independence assumption, the number of matches is a random variable. Okay, so like I think Donovan was saying, like the number of matches could be any number from 0 to 100,000. Okay, what exactly the number of matches is a binomial random variable, okay, with parameters 10 to the 5 and 1 over 50,000. Okay, so does everyone see the connection between this question and what we have been asking? Okay, so this is what, so why, so we know what the probability, so we know the probability y will be exactly one match. What's the probability y is 1? Right, so the probability that k matches is that, so exactly this, so this is 10 to the 5, choose 1, times p to the, right, p to the 1, 1 minus p to the 10 to the 5 minus 1. Right, we also know the probability y is exactly 2. Okay, so right? And so on. Okay, we know the probability y equals 0. Probability y equals 0 is 1 minus p to the 100,000. Probability y equals 10 to the 5 is p to the 10 to the 5. Okay, so we can write the probabilities of all of these values. Okay, now when you look at it, right, it's not terribly instructive to just write these probabilities. That's not the way we think, right? Because the very first statement that you said was, on an average there are two matches, right? And this is what we want to capture with expectations. Okay, we want somehow to write the we want to exactly get to this number 2. Okay, and in fact here the expectation of y is 2. Okay, so we want some sort of but these numbers, right, not to uh, in this form, right? So and this is not a, this is like a subjective statement, it's not a very objective statement. When we look at these numbers, they don't make much sense to us. Okay, that's all it means. Okay, what we would like is something that captures how y behaves. Okay, so we want instead we have been thinking of an average value. We have been thinking of an average value for y, but when you took the average value for y, you didn't just add up all the values y could take and divide by the total number of values. Okay, that would just be 50,000. Okay, that would be something close to 50,000, right? That is not something that is useful. Okay, plain average of the values that y can take is not what is useful. Okay, what you want is to say something like, on an average y will be 2. Okay, and you get that average by the definition of expectation that we had. Okay, and what is so remember, we don't want a plain average. Okay, and by plain average we mean 0 plus 1 plus, so these are all the values y can take. These are all the values y can take. There are 10 to the 5 plus 1 values like this. Okay, this average is not what we want. Okay, this is kind of useless. It doesn't tell us anything about probabilities. Okay, so instead we need the expectation of y. The expectation of y is simply the sum uh, over all the outcomes in the universe. The outcomes in the universe are all sequences of all binary sequences of length 10 to the 5. Okay, the probability of any of these outcomes times the value of y for that outcome. This is what we want. But when you think about this, and we'll do this simplification without proof, okay, but it's something that you can figure out easily by thinking about it. Instead of always summing over the outcomes of the universe, you can choose to sum over the values a random variable can take. Okay, so you can choose to sum over the values y can take. Okay, and you can write the probability y equals, okay, and okay. Okay, now this is something that is always true for any random variable, right? So instead of summing over all the outcomes of a universe, you can just sum over the values the random variable can take. Okay, and take the weighted average of all those values. Okay, y can take values k, where k ranges from, so let me write it. Okay, y can take values k equals 0, 1, 2, 3 to 10 to the 5. Okay, so this is what we sum over. Okay, so we would write expectation of y equals 0 times the probability y equals 0 plus 1 times probability y equals 1 plus 2 times probability y equals 2 all the way to 10 to the 5 times probability y equals 10 to the 5. Okay, so instead of just adding up all this, instead of just taking a plain average, we weight every value that y can take by the probability. Okay, so we take a weighted average. Okay, now at this point it is still hard for us to compute because this summation is something like k equals 0 to 10 to the 5 k times 10 to the 5 is k p to the k 1 minus p to the n minus k. Okay, now this is something that you can compute without too much difficulty, but we haven't in this class, for example, we haven't paid too much attention to binomial sums and everything. Okay, so we don't know how to do it, but lucky for us, we are not trying to learn combinatorics, we are trying to learn probability. Okay, there's a simpler way to see this summation, but for example, is everyone clear about what we are trying to do? We are looking at y, okay, and we know what's the probability. Y can be any number. Okay, so in this town with 100,000 people, okay, so like if the judge asks, okay, how many people are likely to match, right? If I start saying that the probability there is 0 matches is this, the probability there's 1 match is this, the probability there's 2 matches is this, and so on, okay, it's not going to really argue for your case. Okay, it doesn't really make much sense to many people. Okay, instead we want to capture a succinct representation of this random number. I want to be able to tell the judge exactly what you told me. Okay, that on an average there'll be 2 matches. Okay, and to get that, what I do is I create like a notion of an average for y. Okay, and it's not a plain average because the plain average doesn't capture anything about their probabilities. Okay, so instead it's the average like this. I take every value y can take and I take the weighted average of those. I weight every value y can take by its probability. Okay, by the probability y can take that value. Okay, and this weighted average is what I call the expectation of y. Okay, so here so we are almost done, but I know we are out of time, but it will just take a couple of more minutes. What I can't compute y, but can I compute expectation of x1? X1 is the probability, X1 is the, remember X1 was the random variable that said whether person 1 matches or not. Okay, X1 is 1 if person 1's DNA matches the crime scene, 0 if it does not. Okay, what's the expectation of X1? So X1 can take values 0 or 1. X1 can only take two values, 0 or 1. Okay, and I want to take the weighted average of those two values. Okay, so x1, the expectation of x1, I'd say 0 times the probability x1 equals 0 plus 1 times the probability x1 equals 1. Okay, and this is obviously 0. I don't even have to worry about the this term is 0 because I don't even have to compute the probability x1 equals 0. So this is just the probability x1 equals 1. Okay, the probability the first person's DNA matches the crime scene is 2. Okay, which is 1 over 50,000. Okay, everyone okay with this? Okay, what is the expectation of x2?
If they're independent, it would be the same, right? 1 in 50,000.
So it's the exact same calculation. Okay, and same with expectation of x3 and Same with expectation of x 100,000. They're all the same. It's exactly 1 in 50,000. Okay, but y is expectation of x1. So y is x1 plus x2 to 10 to the 5. Okay, but this expectation is a linear function of y. Okay, we never take a y squared anyway. Okay, we take all these values that y can take, multiply, take a weighted average. The average is a linear function. Weighted averages are linear functions. Okay, so and that is the crucial insight that has this. Y is a linear, the expectation, the weighted average right? So we'll have that the expectation of y is x1 through x10 to the 5. It's simply the weighted average of each of these individual random variables. Okay, now every single expectation we know is 1 in 50,000. And there are 10 to the 5 terms, right? So this is 10 to the 5 divided by 1 in 50,000, and this is 2. Okay, so the average, the weighted average of y is in the 2. Okay, we'll continue the last part of what we did next class too, and we'll do many other examples of this. Okay, and this is what it truly means when we say on an average there will be 2 people who match. Okay, so it does not mean that so it means that the number of matches could be actually any number from 0 to 100,000. Okay, but the weighted average of all these numbers, of all the number of matches, is 2. Okay, so here it coincides with other things. Okay, so it coincides, 2 is also the most likely value for the match. Okay, in general the expectation need not be equal to the most likely value a random variable can take. Okay, but in this case it also is, so it's kind of very nice. Okay, so we'll stop here and continue next class, but you can continue asking questions.